We're going to get through chapter 6 really quick. Chapter 6 is a matter of getting through momentum, impulse, force, and velocity. So here we go. So the objectives for the first section should be able to compare the momentum of two different objects. Fairly simple. The one with more velocity should be the one with more momentum. The one with more mass should be, again, have more momentum. Now, that being said, you should be able to go through and calculate each one by the end of this section. So, linear momentum. Short version, it is mass times velocity. Understand, velocity has to have a speed and a direction. That is what makes it a velocity. If it doesn't have the direction, it is just a speed, it does not give you momentum. That's also why momentum is a vector quantity as well. So, has to have those two. If you don't have the equation momentum equals mass times velocity, you need to add it to your notes. So, force over time gives you an impulse linear momentum. You should be able to remember this. Very rarely will we have any time that is 0 or a time that is 1. You can go back through the theorem. This is where you start linking chapter 4, chapter 5, and chapter 6 together. If you have a net force, then you should have a change in momentum, and we'll go through that equation right now. Force times time. Example, as we saw with the net force, you had to find a force moving an object left, right, up, down. So that would be force times time gives you your change in momentum. Again, at the bottom of the screen, force time to time interval gives you your change in momentum. Also, kind of a helpful equation is force times time equals momentum. That also equals mass times velocity final minus mass times velocity initially. Again, should be a good equation to have. Bottom of the screen, make certain you copy it into your notes. Okay. Linear momentum. Stopping times also depend on this. Force reduces. Now, here's where we have fun. And I will tell you, this is where we'll go through a little bit of equations. If I take a student, I don't know which one you could pick who you want, and I take them, spin them around a circle, and then I stop them abruptly, like running them into a wall. In that case, the stopping time is very, 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 very small. Fraction of a second, right? But I'm not that mean. You know this. So here we go. We're going to take and we're going to run that same student into a wall, but wait, there's going to have like 4 or 5 feet of pillows in front of them. The stopping time is now, instead of a fraction of a second, it is a couple of seconds. The time it takes you to stop is a lot greater. Example, say instead of a fraction of a second, you have 3 seconds, 4 seconds. Well, that is how force is reduced, how injuries are reduced. If you think about your car, it's a simple argument of why we invented the actual airbag. It actually slows your head and shoulders and body down in a second instead of the steering wheel, which is a fraction of a second and causes damage. So, another example, bottom bullet, force is reduced when time of an impact is increased. Again, force times time equals your momentum. So, very simple. Ow. Law of conservation of momentum. This is a short version you'll figure out in college. It is not exactly true. It is a law. However, there is a whole bunch of, well, what about what ifs? So, law of conservation of momentum, very quick. Total momentum of all objects has to remain constant between the starting and ending velocity. So, this is the equation. Initial momentum of the first object, mass and the velocity of the first object initially, plus the mass and velocity of the second object initially, has to equal the mass and velocity final of the first, mass and velocity of the second. Total volume. Sample problem. Take a second to copy down your variables. So you have a mass, initial mass of the boater, an initial mass of the boat. If the boater steps out of the boat and she steps onto the dock, if that boater is moving at a velocity of 2.5 to the right, final, what is the final velocity of the boat? So you should have wrote down mass 1, 76 kilometers, or 76 kilograms. The initial velocity of her, just standing on that boat, is 0. Mass of the boat is 45 kilograms. The velocity of the boat is 0. Velocity of her is 25 meters per second to the right. That is important. It has to have a direction. So now I plug this in. Again, there's your equation. The book's version, you plug it in, you move all the algebra and then plug it in. I like to do the math first. Now, the answer you get is technically a negative. Negative 4.2 meters per second to the right, because our label is previously to the right. Not a fan. So we said a negative to the right. Or you can just go, hey, that negative and to the right means it's really going where? 4.2 to the left. Should make sense. All right. Opposite, therefore it's to the left. Good. Newton's third law. During a collision, force on a bumper car, you guys already understand this. The faster you go, the more impact you can put to another person. Hopefully you've all done bumper cars. If not, you can make that a homework assignment. Go play in bumper cars. Study physics. So, the faster you're going, the heavier you're going, the more impact you can have on another person. The total momentum is still the same. Understand, the total momentum is still the same. Your energy is transferred to another person's. So, perfectly inelastic collisions, really get into your brain the definition of perfectly inelastic. So, if two objects stick together. So, example, initial momentum of the first object, initial of the second. When they stick together, you can add the masses and their velocity is the same velocity. So, total final momentum. Sample problem. One clay ball, mass of 0.5 kilograms, initial velocity of 4 to the right, second ball of 0.225, velocity to the left. Understand one of those has to be negative, one has to be positive. Give you a second to write down everything. You might want to pause the video. So we have those written down. Should look a lot like that. I'm going to say to the right is a positive, to the left is a negative. You'll often do that. Right's positive, left's negative. Then we use our equation. Now notice that the question does ask to find the kinetic energy. Well, that's our change in kinetic energy, but we don't have the final velocity of the two balls stuck together. So that's the equation we're going to want to use, except the big problem is we do not have the final velocity of the two balls stuck together. So first thing we have to do, find the velocity of the two balls stuck together. Now again, this is an equation that is modified. Mass of 1, mass 2 should really be over here. That's okay. Again, they use algebra to solve the equation first and then plug everything in. Me personally, I like to do all the math I can before moving the equations around. So should have a velocity of 1.67 meters to the right of the two balls stuck together. That being said, again, going back to the question, it is just looking for kinetic energy change. We just found velocity. That is not the final answer. So we have to put it into the equation. Initially, 4 meters per second to the right, -3, meaning it's going to the left. Initially, the system has 5.12 joules of energy. Now the final, this is what we just used to find 1.67. Stick the two balls together, 1.67 squared times the mass together times 1/2. The last step, you subtract the two, you get a -4.07 joules. So energy is lost. Should make sense. You have two clay balls moving very fast, stick together, will form one. That one is moving slower, has less kinetic energy. All right, hopefully you have questions on that. Elastic collisions, total momentum is conserved. Most of the time we have all the equations for this, all your energy will be conserved. So, in this case, all the energy from the first two go in and come out as energy in the second two. kind of what we did in the first one. So, give you a chance to write all these variables down. You might want to pause. All right, let's get going. Your variables should look like this. Mass of the first ball, mass of the second ball. But not velocity initially is going to the right of the first ball. Velocity of the second ball is going to the left, so it's a negative. Final velocity of the first ball is negative to the left, so negative. So we've got everything except for velocity to final. Velocity to final is what we're looking for. So this is our equation. I want to plug everything in. I plug everything in here. The book does it a little differently. I'll show you that part. They do the algebra and move everything around. I'm not a fan. You can do either way. Again, I'll show you in class. I will do the math in on the first way, not algebra. So to me, it makes simple. All right, so you put everything in. Whoop, you put everything in. You find your velocity is 9.0 times 10 to the negative second meters per second to the right. Again, you can check your math. The hardest part about this math I'll show you is right there. Understand you have to subtract over a negative, which is really adding. So, all right, elastic collisions. Finally, one of the things they're big on in this chapter is checking your work to make certain it makes sense. So in this case, kinetic energy initially, kinetic energy final. So you have the velocity of the first ball, velocity of the second ball, gives you total kinetic energy of 8.7 times 10 to the negative fourth. Second part of this, velocity of the first ball after the collision, velocity of the second ball after the collision. Same energy. No energy was lost. Should make sense. This is one of the pages, I'll tell you right now, don't copy this down. Go on page 220 of your book. Again, page 220 of your book. Copy the chart on page 220. It's a little bit better, shows you a little bit a better equation. So, and that's it. What I would recommend is going in, starting practice problem A, practice problem B. There's 1 through 3 and 1 through 3, I believe, on both sections. Good luck, I'll see you in class.